Okay, so we pick up part 2 here at example 3. We talked about in the first half of the lesson, we talked about what a relation is, right? An expression of something. Usually there's a variable in there, so something that can change is an expression. So how fast you can or how far you can go, it depends on the time that you walk and the rate at which you walk, right? An equation has an actual equal sign in there, and then it involves two variables. So one variable equals usually some other variable with some other operations attached to it, and you get an equation. So we have some examples of those. Here's our equation right here for our last example that we did. The number of people that can fit around tables would be 2 times the number of tables plus 2. And so if we have 6 tables, we can seat 14. If we have 10, we can seat 22. And 25 tables, we can seat 52 people in this arrangement. So this is what we finished doing. What we haven't done yet is looked at a table of values, looked at random points, and tried to come up with an equation for these points. We are studying linear relations. So we talked about yesterday that linear relations and linear equations would be relationships between two quantities. And I do this because this is the x horizontal axis, this is the y vertical axis. And relationships or mathematical equations that we are studying here relate two variables. This variable, which might be something like time, okay, and this variable, which might be something like the distance you travel, right, for that example. And so a linear relation would have a graph, a collection of points that would be a perfectly straight line, linear relation, which means that it's pretty easy for us to write an equation by looking at the points. So we're up to speed here now. So if you remember from yesterday, there's a couple things we want to look at. The easiest types of tables of values to determine a linear equation from would be where one variable, and this would be the independent variable. Usually the independent variable goes on the left, okay? Because table of values, if you remember from last year, or from learning this, it's usually like x, y, like this, and x is on the left. X, the horizontal axis is x, the vertical axis is y. And so the independent variable goes down on the horizontal x-axis, and the dependent variable goes here. Because we go ahead and we look at this, and then we measure something and plot the point. Look at this, we measure something and plot the point. So usually the first column is the independent variable, usually. And if the independent variable goes up by 1 each time, I'll just zoom in just a bit here. So if this goes up plus 1 each time, this makes this really easy to find out part of our equation. So this is plus 1 each time. I know it doesn't have to do that, but if that does, then all you need to look at is you need to look at by how much this dependent variable goes up by. And 3 plus 4 would be 7. And then we do plus 4 here. And as long as these points here, these numbers here are separated by the same number, we know we have a straight line. So if all these numbers are the same and then all these numbers are the same, we have a straight line relation, okay? And the big part of the linear equation is the slope of the line. Now we haven't talked about slope yet, but it's the number that multiplies by one of the variables, okay? So from yesterday, we take a look at this number and we write this number divided by whatever this number is, and it just happens to be 1, so that makes this easy. And so the number of people, or the p, whatever the people is, or p is, doesn't really say. So p would equal, this is going to be 4 over 1, or just 4n. Okay, that's where we start in building our equation. So again, if all these numbers is plus 4, plus 4, plus 4, plus 4, they're all the same. They don't have to be 4, but they have to be the same from each other. And these ones are all the same. Then we can do this number divided by this number, and that's going to be the number that multiplies by our independent variable. Okay, now, if you remember from yesterday, we have to check one more thing, because this might not be the whole equation. This could be the whole equation, but we now have to try and test some points to find out if there's anything we need to add or subtract on the end, because that's usually what we might have to find a number to add or subtract on the end here. So how do we get from 1 to 3? Well, let's try this out. This is the way I would do this. Oops, sorry. 3 is what I need to end up with, and n is what I start with. So let's say, is that equal? Because this is the n value right here, and this is the p value. So does 3 equal 4 times 1? It doesn't. Okay. So how can I change this side to make this side equal to 3? The first thing that comes to your mind, you say, let's try and subtract 1, because 4 minus 1 would give me 3. Okay? So that's just where you start. You pick a point, and you use the part of the equation that you've kind of figured out from the changes in the variable in the numbers, and then you kind of figure out, hey, what can I add or subtract to make this? Okay, this one works for the first one. Let's try the other ones real quick here. So I'm going to go down to 7. So 7 is the p value, and that's associated with 2 as the n value. So now let's run this possible equation. Does this work? Well, 4 times 2 is 8, minus 1 is 7. Oh, that works too. Let's try one more. Let's try the last one. So I'm going to put 19 over here, and I'm going to put 5 for my input variable. And 4 times 5 is 20, minus 1 is 19. Okay, so it seems like the points that we're checking works, and that should work for every point that's listed there. It should work for every point. So what that means is the equation is 4n minus 1. So p equals 4n minus 1. All right. Anybody have any questions about how we kind of built this equation? The number that multiplies by n comes from this right here. And if this is not 1, you'd have to go 4 divided by whatever this number is over here, because it's possible that this could not be 1. Okay? And then this would be, just the adjustment that we have to make. Okay? Sometimes there's an adjustment that has to be made. And that's going to be the type of equations you're going to have to figure out, just like that. Okay? Nothing really more complicated. There's not going to be an n squared, or there's not going to be a cubed or a square root or anything silly like that. These ones are linear. That means that we have n to the power of 1 only. That's the type of equation. Okay? All right, let's move over to B. Let's move over to B, and we'll start at the exact same place, and let's see what we find over here. Okay, these are plus 1. Okay, this is plus 1. That's awesome. Each one is separated by 1, so that's going to make the first part pretty easy. I have to figure out what separates these two numbers. What's 7 minus 4? Right, so I add 3 to 4 to get 7. And then over here is plus 3 as well. Plus 3, plus 3. Awesome. Because all of these numbers, they're all the same. These are the same, and these are the same. That means I have a linear equation. It's a straight line equation. Okay? That's what that means. So I highlight this 3 here. I highlight the 3, and that we know now is going to be 3 times this variable over here, just like 4 was times this variable. So I'm going to have b is my dependent variable on the right, that's the dependent, equals 3 times f. That's how I start. Okay? Don't do 3 times b. Don't say, oh, this is 3 is right with the b here. I'm just going to do 3 times b equals f. Nope. No, can't do it that way. You got to reach over to the first column there. Okay? So now we'll just test and see if this is the whole equation or if we have to make an adjustment. So I'm going to go 3 times 1. 3 times 1 should equal this one, 4. Is that correct? No. What adjustment do I have to make to 3? Because remember, I want to focus on the adjustments on this side, really. What adjustment should I make to this to make these sides equal? I should add a 1, right? This is baby stuff, right? When you take it one step at a time and you start to think this way, okay? And this is why I'm doing this over and over again, so that you guys can get into a pattern, that you can get into a groove. You can do the same thing every time. Your brain gets used to thinking this way, and this becomes easy, right? Because once you do, and I've been doing math for 3 decades here, so and this is what I still do when I work on my university level calculus over here that I'm teaching the grade 12s. I do it over and over and over and over and over again. I wake up in the middle of the night dreaming about calculus. Okay? Now, I don't wish that on anyone. But in order to be good at something, you got to do it over and over again. You got to establish good patterns, and you just got to practice. That's why I give you homework. Okay? It's not to punish you. It's not to just waste time. It's so that you can practice and get into a rhythm. And you guys know that, I think. You know that. Watched some basketball last night. Our school has some great basketball teams. And you know what? I know how much practice those basketball players put into their free throws and into those plays that I see them run. It's over and over and over again, right? And if someone's being lazy, what does the coach do? Hey, let's go. Hey, get in there. Do it right. So I don't know if I've told you this yet, but I'm like your math coach, okay? Think about this as our math team. I'm your math coach. So when I come around and say, hey, this is not good enough, show your work, circle your answers. I can't read that. What is that? Fix it. I'm your coach, okay? I'm just trying to make you into a better math player, all right? And everybody wants to be a better math player, right? I know. Okay, so that's why I'm trying to do this over and over again to get you into the routine. Okay. Now, where was I? I had to preach there for a little while. Okay, so I've got 3F. Oh, I've made an adjustment plus 1. So 3 plus 1 is 4. Let's test some other points there. I'm going to pick 10 and 3. I'm going to pick 3 and 10. Okay, so 3 times 3, and then I got 10 over here. So does 3 times 3 plus 1 equal 10? Yeah. Oh, that's good. Let's try one more, just to be sure. I just want to be really sure here. So I'm going to pick the last one. So 3 times 5 plus 1 should equal 16. Let's see, that's 15 plus 1, 16. Is everybody good? Okay. So I'm going to put a plus 1 here, and that should relate all the variables on the one side of the table to all the variables on the other side of the table. And it looks like that should be our equation. Okay, any questions? All right, example 4 says, this should be the top of your next page, I guess. An airplane is cruising at a height of 9,000 meters. 9 kilometers up. Is that even real? The table to the right shows the height of the plane every minute after it begins to descend to land. Okay. So I think about graphs. We haven't really talked about graphs too much. I think about graphs, okay? As time marches on, the height here is going down, okay? So as this variable, am I going the right way for you guys? As this variable increases, this variable decreases. You see? That's like an opposite relationship, okay? Like an inverse. So a lot of times, both variables grow and they both increase. Like the time it takes for you to walk to school or whatever, like the distance you get away from home increases as time increases. This one, the plane starts really high, and then as time goes on, the height above land goes down. So you've got some graphs are going like this, some graphs are going like this. Okay? And if over time nothing changes, that's a graph that's flat, right? Because nothing changes on the other side. Just time changes. This one doesn't change, let's say. All right, so the plane is coming down. So we're going to see a little bit of a different equation here. And I want to see if you can spot what the difference is when in this relationship. And I'll just sketch right here, okay? Just a quick sketch here. We've got a plane starting at 9,000. You don't have to write this, you can, but 9,000, and it's coming down over time. You see that? That should be a straight line. And as time marches on, this value on this variable, this quantity, comes down. So that's going to look like that. The one before, let's see. So these ones that we did with these equations, this was going up. It was kind of like this, okay? Going up. This one also going up, okay? That's kind of what they look like. They're going up. This one's coming down. Okay. Write an equation that relates the height of the plane to the time. Hey, no problem. No problem. Because this goes up by 1 each time. Plus 1. Awesome. What happens here from 9,000 to 8,700? What's that change? 300. 300? Anything more? Just 300? Thank you. It's going down 300, so minus 300. Yes. Very good. That's actually really important. Is it going down 300 again? Yep. And again? Yeah. Okay, so you see what's happening here. This number A is very large. Doesn't matter. Equations don't care if the numbers are large or small or whatever, fractions, decimals, who cares? And it's negative. So, write an equation. We got to go 300 times t, right? Or negative 300 times t equals h. So I'm going to go h equals negative 300 times t. That's the first part. Do I need to make any adjustments here to this? Do I need to add or subtract something to this? Because that's what I'm looking for now. So let's test out some numbers. So I'm going to go negative 300 times 0, because that's the first one, equals 9,000. This is actually a good one to check because the adjustment might be pretty obvious here. Because negative 300 times 0, guess what, is 0. So what adjustment do I have to make to get to 9,000 from 0? Plus 9,000. Okay. Well, that's a really big number. I don't know if that can be right. What do you think? Maybe? Well, let's keep checking. Let's keep checking. Okay. I'm going to change these numbers. And I'm going to go to the next one. 1 and 8,700 over here. So let's see. Negative 300 times 1 is negative 300 plus 9,000. That's the same as 9,000 minus 300. Does that equal 8,700? It does. It does. Okay. One more. Let's just do one more. I'm going to take the second last one. So 3 here and 8,100 here. Okay. So this is going to be negative 900 plus 9,000. Does that equal 8,100? Yeah, 9,000 minus 900 is 8,100. So we have got a winning formula here. I need to add 9,000 to here. And that's my equation, or our equation. Okay, I'm going to pause right now, and I want to see some fingers here. 5 out of 5 means you completely understand this, and this is going very well right now. 0 out of 5, you're not speaking my language at all. Okay, so where are we? Oh, good. I see a lot of fingers. I see a lot of fingers. I see a lot of 4s and 5s. That's great. Okay, that's great. It's because you guys are so smart. That's what it is. Okay, let's see about B here, though. What is the height of the plane after 15 minutes? I guess we can't figure that out because I don't have 15 on my chart. There's no 15. So I guess we skip it, right? No? Okay. How do I figure that out then? Okay, I'm hearing a lot. Okay, hearing a lot of stuff here. Okay, so should I add to this chart? Should I add numbers to this chart until I get to 15 here?
15 is the variable.
So I should use my equation. That's why we need an equation. That's why we have an equation. You could, if it was like 5 minutes, like, hey, what's going on at 5 minutes? Well, you could just subtract another 300, no problem. But this is a waste of time, filling on all this chart. We don't need to do that. And again, in math, we're trying to be smart about this stuff, and I'm recognizing a pattern, writing the explanation, and I'm going to use that explanation, right? So this is how easy this is. This is how great math is, okay? So 15 minutes, that's going to be in place of the t variable. See that? So negative 300, I'm going to put 15 in here. And I'm going to keep the rest of my equation, don't forget about that. And that's going to equal h. So h now is going to be defined by this mathematical statement right here, this expression. So what is, and you know what? Feel free to get your calculator out if you need to. Okay. Negative 300. This isn't as bad as it looks. Like, you can just do 3 times 15. You don't have to worry about the zeros. 3 times 15 is 45. That's a negative 45. And add those 2 zeros onto it. 100. Negative 4,500. Okay? So there we go. Didn't need a calculator. Okay. Negative 4,500 plus 9,000 equals h. So h equals what? 4,500. Now, it says what height is the plane. So if I just circled this, would I get full marks if I just circled that? No, I wouldn't. Why? What did you say? You need a, okay, I just didn't hear that. Am I hearing units? Someone saying units? Units. A sentence, oh, did someone say sentence? Sentence is a great idea too, yes. So units and a concluding sentence would be the perfect. So plane is 4500, 4500. What is the units there? How do I find that? Oh, hey, here we go. Meters. 4,500 meters above ground. Above ground, right? Because that's what that's what this example's talking about, right? So the height of the plane above ground. There you go. Plane is 4,500 meters above ground. Fine. If you put at 15 minutes, that would be the best possible concluding sentence. All right. We're getting somewhere. Questions? Okay, we're getting pretty close to the end. I think this is the last page. So we've got a few questions. One more question left on this one, and then we'll do one more example, and then we'll be done our lesson today. So how long after the plane begins its descent does the plane land? Oh boy, now it's getting real. Now it's getting real. How long after its descent does the plane land? Okay, this is actually really important for you guys to understand what's going on here. We have to connect this sentence with the situation and the equation. So remember what this question says. You have to go back and look at the question and remind yourself that this is minutes after it begins to descend, okay? Minutes after it starts coming down. So how long after the plane begins to descend? We're looking for a t value. So guess what I'm going to do from yesterday? T equals, I don't know. Wow, I got 2 extra. T equals, don't know. How long after the plane begins its descent does the plane land? So T, I don't know. What am I given here in this question? What am I given? There's no numbers there at all. It doesn't say anything about height. What can we gather from this sentence? What am I given? It's a tough one.
Your answer should be 0.
What should be 0? 0? You saying something should be 0? What should be 0? Oh, the height should be 0. Why?
Because you land on.
Oh. So when the plane lands, safe landing, everyone. Remove your seatbelts. So when the plane lands, it's 0 meters above the ground. If we're just kind of like, we're talking about the bottom of the tires, I guess.
Yeah.
Not the people. 3 meters above the ground, whatever. Yeah.
15 minutes, it's halfway through its descent.
Oh, okay. I like this thinking too. Okay, so let me just, okay, H is 0. When H is 0, good. Okay, H is 0, so that is a given. Now, I just heard that 15 minutes from B, 15 minutes after it's descended, it's exactly halfway to the ground. Look at that. 4,500 is half of 9,000. That is amazing thinking as well. So what might be your guess before we do any math here? Any more math? What might be your guess? Half an hour. 30 minutes. That's top shelf right there. That's good. That's top shelf where mama hides the peanut butter up there. That's good. Oh, that's another old saying, yeah. We're doing the old sayings week. This is old sayings week. Let's see. Where mama hides the peanut butter. And I think it's because the kids like to get into the peanut butter and they can't reach the top shelf. That's like so special. That's special. Okay. All right. That math thinking is like equal to special peanut butter. Great special peanut butter thinking. Okay. All right. Well, let's see. Let's do the math and let's see if that's going to work out. So H is 0. I've got negative 300 T plus 9,000. Okay. All right. Well, I've got T buried in there somewhere. Now, you should know how to do this from grade 8, and this would be a good time to kind of practice and talk about how we solve for T. You could maybe think about this mentally. I don't know. You could probably just run a few options for T and say, maybe 10, maybe 20, maybe 30, maybe 40. You could just do some trial and error, I guess. But you guys should remember that in order to solve for an unknown variable that's kind of inside an expression somewhere, we want to try and isolate or get that variable all by itself. And so we talked a little bit about this yesterday. If we get everything to the other side of the equation and isolate T by itself, we're going to solve for it. So I am going to subtract 9,000 from both sides. What we do to one side, we have to do to the other. And I'm going to have to go over here because I'm running out of room. I'm going to have negative 9,000 equals negative 300t. This 9,000 and that 9,000 are going to cancel out, right? So negative 9,000. Now what I need to do is I need to figure out what value t is. And so I'm going to do the opposite operation that I see happening to t. And the opposite of multiplying is dividing. So to each side, I'm going to divide by negative 300. And this is the algebraic way to solve for t. Instead of trial and error and guessing, and this is what you're going to need to practice and know how to do as you move through math in high school. If you can't do this, if you're just guessing all the time, you're not going to go very far. You're not going to do very well. It's going to be frustrating for you. So this is going to help you. T equals. Now, a little shortcut here when you're dividing all these zeros. So that 0 can like go with that 0 because that's a factor of 10. That 0 can go with that 0. What's 90 divided by 3? 90 divided by 3 is 30. And yes, you can do that in your calculator if you need to. 9,000, negative 9,000 divided by negative 300 is 30. Awesome. So I like the rational thinking over there. That was great. That turned out to be the correct answer. And I should probably check that. So I should probably go, where's my formula? H, so 0 equals negative 300 times 30 plus 9,000. And this is my little check here, just to make sure everything's going smooth. So that's negative 9,000 plus 9,000 should equal 0. That is totally correct. Okay? So 30, I should make sure I put minutes there, 30 minutes, and a sentence would be best. So 30 minutes after the descent. So plane lands, 30 minutes after beginning descent. Descent. Is that SC, right? DESC, correct? Yeah, DESC. After beginning descent. And to descend means to go down. Okay, now these questions do take a long time. It's gonna take you half the time because I'm not stopping and telling stories and explaining things and asking you questions and being goofy. But it's not gonna take you this long. But it's not gonna be like 2 seconds and you can move on. You're gonna have to think about problems for a little while. And that's part of the reason why I think students don't like word problems. It's just simply because you gotta stay focused. It's tough for us to stay focused. And one step leads to another, which leads to another, which leads to another as well. And finally, the third thing is the words, translating that into mathematical equations and statements. So this is your time to practice, okay? Shoot those free throws, one after the other. Just keep practicing this stuff, and you'll get good at it. All right, I am going to give you guys a chance to do example 5 before I give you the rest of the assignment for 4.1. So I want you to see if you can carry example 5 all the way through to the end, and then I will show you the answers here once you've had maybe 5 minutes to give this a try, okay? So 5 minutes for example 5. Try and show your work just like I've done. Circle your answers, make sure you have your units, including sentences, do your checks, okay? Try and do everything the way I've been teaching you to do that. Take a little bit of time to do that, and we'll see where you are after 5 minutes, okay? Okay, so in example 5, to get you going, this fixed rate here, okay, what you want to remember is when we had the table of values, when we created our equation, we had an adjustment that we had to make. So we had some number times a variable, and then we had to adjust something. This is the adjustment. As soon as you get in the cab, you owe $3.60. Then the price goes up $1.50 for every kilometer that you drive. So write an expression for the cost of the ride of the cab. Well, we have $3.60 is our fixed rate, and then we add on to that $1.50 for every kilometer, per kilometer driven. So that's like $1.50 times, okay, I'll just use K, it doesn't say, I'll use K for kilometers, okay? So that's the expression for the cost of the cab ride, $3.60 plus $1.50 for every kilometer, or $1.50 times kilometer, okay? Now, I guess I'll just keep going here. Some of you guys have got into this, but I'll just keep going. So, is everyone okay with that, with A? Okay, fixed rate, that's like the adjustment. Okay, and if you want to write it like we wrote the other ones, you could just switch these around. 150 K plus 3.60 plus 360. So there's your adjustment here. Okay, the fixed rate is like the little adjustment for the price. Now, the equation for the total cost, this is just adding an equal sign and another variable. So cost will be our second variable, and probably be a good idea to make cost equal to C. So that means that C, the cost, equals this expression right here. And I'll put the variable term first. And do you have to put the dollar sign? No, you don't have to put the dollar signs in your equation. Usually the units are not included in the equation, so you can eliminate those. So a purely mathematical equation would just kind of look something like that. But we would know that we're dealing with dollars, so at the end we have to make sure we have dollars and we have kilometers as the other unit.
You can drop those zeros too, right?
Well, because we're dealing with money, it's a good question. Because we're dealing with money, you should keep 2 decimal places, because again, it's not completely right even to say, you know, like $3.7. Because it's dollars, then we should put the second zero there for all the cents. So, yeah, technically you can drop this last zero, but because it is dollars, we'll probably retain that much anyways, just to remember. Okay, all right. So what is the cost of a 12-kilometer cab ride? So I'm given 12 as the K. So K equals 12. I don't know what C is. That's the cost I'm trying to find. Couldn't be much simpler than that. I'm going to put 12 in for K, and then I'm going to find out what C is. So C equals 1.50 times 12 plus 3.60. So that's going to be, cost is 18 plus 3.60, which the cost here is going to be then $21.60. Okay, so the cost of the 12-kilometer ride is $21.60. And yeah, you don't have to put that dollar sign just there with the math. I guess you could just make sure you put it there. It isn't incorrect to put your dollar signs throughout the question. That's okay too. All right. Anybody have any issues at all with example 5, or any questions about example 5 that I can help you with? The other thing I'll say, the word fixed in fixed rate, that means that this doesn't change. That dollar amount doesn't change. It's fixed, as opposed to variable. And so what changes is this 150 times K. That part of the cost changes per kilometer. So the fixed rate it does not have a variable attached to it. It's always the same. So no variables with fixed things. Okay? So including the assignment I gave you yesterday, that was 3 to 9, I guess. So now you have 3 to 10, 14, 15, and 16. And yeah, 14, 15, and 16 are word problems. So they're going to take a little bit of time. All right, we have some class time here today to work on those. And so you can get started on that now. Any questions before you get going on that?